So let's talk about some definitions when dealing with inner products. So one definition that we have is something that's orthogonal. Uh, so you're probably used to that in other classes, this idea of orthogonality. We mostly talk about it in terms of things like coordinate systems. So if we have an x and y axis, we say that x is perpendicular to y, or really they're orthogonal. What orthogonality means is that if we think of these now as vectors, that a vector that lies along the x-axis, well, that was pretty bad, that no component of that vector is going to be in the y direction. So the vector is only in the x direction, and it's orthogonal to the y direction. So basically what that means, if you kind of think about it in the unit vectors, so if we took the I unit vector and we dotted into the j unit vector, then we should get 0. So I and j unit vectors are orthogonal to each other. And the same is true for the inner product. So if we have some inner product of v and w, we're taking the inner product of these two linear vector spaces, the v space and the w space. Those two linear vector spaces will be orthogonal to each other if their inner product is 0. So that's the first definition. The second definition is the norm. So with the norm, basically that's the length of the vector. So again, we're kind of used to that. If we take two geometric vectors a and b, and then we take the dot product, then what we're really doing is getting some length a along b and some component. So you take the component of b. So if we have a dotted into b with some angle phi in between them, what we're really looking at is that component of, in this case, a, that lies along the direction of b. So we're multiplying the length of the component of a that lies along the length of b. Now the same should be true for vector spaces, that when we can find the magnitude, the length of this vector v, by taking the inner product of v on itself and then taking the square root of it. So this is the norm. So the norm is finding that length of the vector by basically dotting it into itself and then taking the square root. You have to take the square root because when you're taking the dot product of two vectors on themselves, what you're basically doing is finding, in this case, the magnitude of a squared. You're basically finding the square of the length of that vector. So the same thing is true with linear vector spaces. We take the inner product of v and v, and then that gives us the length of the vector squared, and then we take the square root of it in order to get the norm. So if we put those two concepts together, we can have our third definition, which is something that is orthonormal. And that's a condition that we're going to look for in quantum mechanics. And so orthonormal is if we have a set of basis vectors, basically unit vectors, and we have a unit norm. So if we were to find the norm by taking the square root of the inner product, then that is going to be equal to the unit 1. So we have basically a unit vector from that. And it's orthogonal to other basis vectors. So basically we're looking for basis vectors that are orthogonal to each other, and the length of those basis vectors is unity. It's a unit norm. So that concept of orthonormal or orthogonality is going to come up time and time again in quantum mechanics. So we'll come back to that a little bit later on. So now what I want to do is kind of turn to an idea of basically these basis vectors. So let's write our vector spaces. Let's say we take V and we find it in terms of a sum from 1 to some dimension n with these scalars multiplied by a unit vector space. So V is the sum of these components, V sub I, which are multiplied by the unit vectors. And then if we were to write W, the linear vector space W, as, again, a sum of a basis vector, so we sum up all the components some scalar, little w sub j, times its basis vector, which I'll write as j. So v is in terms of the basis vector I, and w is in terms of the basis vector j. And so now if we find the inner product of v and w in terms of these basis vectors, then what we have is a double sum. So we have to sum up over the I basis vectors and the j basis vectors. We multiply by these components. Now v, since it's a bra, that has to be the complex conjugate of those components. So we take the complex conjugate of the v components, multiply them by the components of the w vector, and then we take the inner product of I and j. So we're taking the inner product of the basis vectors I, which are the basis vectors for the v vector, and then multiplying them by the basis vectors of j, which are the basis vectors for the vector w. And so now we have basically it's a lot like the dot product, and you'll see that in a minute, that we have the basically multiplying component by component, the v vector components times the w vector components, a lot like the dot product. And we'll see that in the next video about the Gram-Schmidt theorem.